Um, Now we have come to the thrust of economics, optimization. Yeah, the science of optimization actually underpins the whole idea behind economics, eh? And so
Yes.
you need to understand this science of optimization because it shall affect you in all the different courses that you have the minimum and that's microeconomics, macro, and all these other courses. Okay. So now, um, I remember during the what's that piece, that piece was more like a summary of the whole course I told you. So some of the things I will be saying, I think you'll be able to relate with them. We want to talk
Okay.
about optimization. So now, when you're talking about optimization, we are trying to talk about the maximum and the minimums of the functions, nothing much. Okay, the maximum and the minimum of the function. I did indicate to you last time that when you are given a function, let's say you have a function like this, y is equal to x squared plus 2x, maybe plus 5. This is a quadratic function. This function
Yeah. Hello? Hello?
would be
Hello?
a graph.
Sorry, I wasn't able to get you. You went. I don't know if it's network. Hello? Hello?
I showed you that you could easily graph this on a graph, right? Hello,
Yes, sir. Hello?
Okay, can you hear me now? I am here.
Okay, yes, I can get you now.
Oh yeah, so I was saying that this particular function that you have is a quadratic function showing that it has two values of x when you solve it, or two critical points, indicating that if you graph it, it crosses the x-axis twice at 2 points. So that is to say, it could come out maybe like this, or when you graph it, it could maybe come out like this. And this is the x or y plane. You remember I
Yes.
indicated this is the x or y plane. So now there are
Yes.
these values, like the value of y here that is here down. This value is said to be the minimum value of y, the lowest the lowest value of y that you can find. Yeah, when you graph this function, where it will cut, that is said to be the minimum of the function. At that point, it's the minimum of the function. But if you are to find the positive values of y, that would be the maximums of the function. You get what I mean, eh? That's the maximum of the function. Then now, having said all this, then you will have these functions having the maximum points and the minimum points. Now, this is the whole idea behind utility. You could now give you an utility function, a utility function actually, and then the utility function that have been given, you could find the minimum point of it and the maximum point. That is basically the highest that we are trying to do. We said that for the costs, we minimize, yeah? And then when it comes to the profit, what do we do with the profit? We maximize.
Maximize.
We max
Yes.
we maximize the profit. So basically, this is just a bit of some science that we are talking about in this course, in this topic. Okay. Now, there are two types of optimization problems that you'd always need to pay attention to in economics. Number one, there is what we call unconstrained optimization and the constraint optimization. And constraint optimization, we are trying to say you want to, for example, incorporate some inputs or factors of production, right, to maximize the output, isn't it? To produce them output or to maximize maybe the profit. Since you are not constrained, we are assuming, I'm here first, we are assuming that you're not limited by any factors. At this point, there is no budget. You're not limited by income. You're not limited by maybe by the prices of these commodities or these inputs. Like there is no limit. We assume that you are not limited. That's what we mean by unconstrained optimization. But when you go down here, it's another conversation now. We assume that, okay, we could have been there trying to desire a lot of things, but now we are limited, right? We are constrained. And then that will bring you to what we call constraint optimization, right? The word constraint comes from the word constraint. Constraint. A constraint is basically a limit. Okay? You've gotten that?
Yes, sir.
So optimization is broken down into unconstrained and the constrained. So with the unconstrained optimization problem, this is the one where you only have an objective function. There's just one function, maybe a utility function that you're maximizing. All right, you're maximizing utility. Or if it's a cost function, you're just trying to minimize cost as much as you can without caring. But when it comes to the other one, it is the opposite. So an objective function, therefore, is the function that you are trying to optimize. Is said to be an objective function. Did you get it?
Yes.
And none of these variables actually are limited or are constrained. So in the general case, a simple case of such functions would be, you have a function y that is equal to, which is a function of different, let's say of different variables, okay? X1, X2, X3, okay? In short, just so many other variables on the right-hand side. It's a function or it's an equation. At that point, you basically just have to solve for these values here and then you are good. Okay?
Kindly repeat what you've said, sir. Sorry.
I said that the function that you have is of the form y being a function of different variables on the right hand side, right? Maybe x1, it could be x2, x3, going up to xn. Or these xx represent the independent variables that are used to determine the output, all right? Or this outcome variable, the y variable. Now, suppose you had these two single argument functions. You have these two single augmented functions. The first one is y, that is equal to negative x squared. You've seen this function, right?
Yes.
If you were to graph this function, how would it come out? This function, if you graphed it, it would come out like this. You've seen it. That's how it would come out. You're following, right?
Yes, I'm following.
You are getting the rationale why it would come out like this. Maybe I should repeat what I said at some point. We said you assume you have an x or y plane, then you have random values of what? X and those of y placed into this function. You could choose maybe, let's say, -2, -1, 0, 1, 2, and 3. These are values of x. We see what values of y they'll give us, right? Let's start. What would be the value of y when x is -2? So you have negative, x is what? -2 squared.
-2.
So you have -4. You've seen, right?
-4.
Then when you have -1, that would still become negative 1 again. And it is
Then
0,
0.
that would be 0. When it will
Then
be 1, that will be negative what?
hmm?
Negative 1 again.
Negative 1.
When it will be 2, that will be what?
Negative 4.
Negative 4. And when it will be 3?
Negative 12. Is it?
Yeah. Yeah, we can just leave it at somewhere negative 2. So what we mean is this. When you graph this function, my good friend, let me use a blow mark. This is the x or y plane for you, right? 0,
Yes.
negative 1, negative 2, and negative 3, right? 1, 2,
2.
and 3, right? 1, 2, and 3, right? And you also have negative 1, negative 2, okay? And the negative 3, negative 4, right? The values of y. Now, what we are trying to do is to plot these numbers randomly. This is that when x is negative 2, what is the value of y?
Negative 4.
Negative 4. Somewhere here you plot, you've seen, eh? When x is negative 1, what's the value of y?
Negative
Is
1.
also negative 1 here. When x is 0, the value of y is also 0. So it will be at this point, when x is 1, the value of y is what? Negative 1, right? When x is 2, the value of y is what? Negative 4.
Negative 4.
So then you can join these, you join these points. I didn't want to really go through all that. This is the message we are sending. You've seen it, eh?
Yeah.
That's what we meant. So now, this point 0, 0 is said to be the relative maximum. This is the maximum point. Like this is the maximum value of y you can always get in this function. That's the maximum. You can't go beyond this, right? But if this function now is positive, it doesn't have a negative, then the minimum, you have the minimum because it will produce a U-shape if you graphed it the way how we were graphing it. It will cut along this. So the minimum value again will be 0. So this is a single unconstrained, function. Okay. Having scored that, it is important to understand that we do observe from the two graphs that the peaks or the troughs occur where the slope of the function is what is 0 at the top part or the pinnacle of the graph. Now that's where you find the critical points. Now the slopes are positive and the negatives to the left and right of the critical points. You find that on these slopes are positive, that is on the left side, and they are negative on the right side. So that's very, very important to score. Okay, now using calculus, are you following? Hello? Do we still have you? Um,
Hello? Hello? Hello, sir. Hello? 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 Hello?
Boss,
Ngwai.
boss. Hello?
Ngwai. Hello, sir.
Where is this now? Hello?
Hello?
Mwenza maenda kuti.
I don't know. It just logged me off.
Oh, you were locked out.
Yes.
Yeah. Okay, let's continue. But you had the graphical explanation of all this that happens, eh?
Yes, sir.
Okay. In a minute time, let's now look at let's employ calculus. We're trying to use graph and what, but let's use calculus because at some point we may not have time to graph, to do all those random values of x. Yeah, it can be.
Hello? Hello? Hello?
Hello?
Hello?
Okay, I was saying we need to employ calculus now to determine whether this function is a maximum or a minimum. This one we already know that it's a what? We already know that
We
it's
know it's a minimum.
it's a minimum, isn't it? And this one, are we sure this is a minimum or is a maximum? This one for the negative, we graphed it from the graph behind. The one with the negative is a maximum. You've seen it.
Okay. Oh, the one with the positive. Yeah, but I've written wrong
Then
one.
this one is a minimum. Okay. Now, let's use the calculus. How do you tell that the function is a minimum or a maximum using a calculus? So you can take the first derivative, for example, take the first derivative of this function and set it equal to 0. Solve for the values of x. So you get the critical value to be x equal to what? to be 0.
0.
And then you also do the same on the other side and set the values equal to 0. So the critical values are zeros. Now listen, when you're done doing that, you can use the first derivative test. The first derivative test simply means the critical value you found it to be what? What is the critical value? This is 0, right?
The critical 0, yes.
So which means when you draw a line like this, there is a line here, 0. We want to test how the function is behaving on the left side and on the right hand side. So we choose the random numbers to put into this. The derivative is negative 2x, right? That's what we've found, isn't it? So we'll be replacing into this derivative different numbers that are on this XOR place. For example, -1, -2, -3, let's say +1, 2, and 3. We just want to see how the function behaves on the right-hand side and on the left-hand side. If we put, for example, -1, what will be the value of the function? The function will be greater than 0, right?
Yes.
2, -1, it will be equal to what? To 2, which is greater than 0. You get what I mean? Eh? So when the function is greater than 0, it means that the function is what? Increasing. Get what I mean? It means it is increasing like this. It's going up. It's rising. And then when you cross now, you pick any number on the other side, the right-hand side, replace by putting 1 in the first derivative, you'll find that the function now has started decreasing. It's -2. So which means the function has a negative, it is reducing like this, which means at this point we have a what? A maximum, because it is curving like this. You've gotten it. This is how to use the first derivative test. First derivative test. You could do the same again to the other one, that one which had the positive 2x. Pick a number on the right-hand side and any random number, -2 or even 1. Put the 2 on the right-hand side and the left-hand side of the critical value. Test how the function is behaving. You'll be shocked to learn that now this one is the opposite. The first one, it goes down and then it starts rising, giving you what? A minimum. Exactly the same thing that we saw in the graphs.
Yes.
Now, we rarely use this first derivative test. It's tedious. It's not very reliable. You get what I mean? Eh? Because the first derivative test is based on our visualization. So you have to visualize and put a vision in your head, how it come out, those things, right? But the second derivative test is master. Is the one that we use mostly. Okay? This one is about using the second derivative, meaning differentiating the function twice. So the steps are number one, differentiate the function, get these steps. These steps, we'll also use them in microeconomics. Please, Napapa, differentiate the function once and set it equal to 0. So for x, set it equal to 0 and solve for what? For critical values. X. You're following, right? The critical values will be x values. Then number 3, when you find the values of x, can you now again differentiate the function again? That is finding the second derivative, right? Yeah, finding the second derivative. That is differentiating it for the second time. And when you find the second derivative, what you're going to do is to get this critical value that you found from the first derivative and substitute it into the second derivative. then you're going to look at the way how the output is. If it's the positive, output or negative output, that is what will help you to determine whether the function gives you the relative maximum or relative minimum. Okay? Those are simple steps I'm explaining. So we can go through. Are you still there? Okay.
Yes, sir.
Now, the take-home message is relative maximum is given when the second derivative is negative. So when the second derivative is negative, then you have the maximum. You got that one? Don't get mixed up. I think I remember at some point when you're doing an assignment, but come at this point to just get a point to use there. Right? Then
yes.
the relative minimum, the function is minimum if the second derivative is positive. It's more like the opposite. These are the ones that you need to remember all the time. Because even if you know how to solve, if you forget which one is, when is it maximum, when is it minimum, people get mixed up as time goes on. Please, we beg of you to be able to remember this conversation. Having said all this, we can continue in the conversation. Now, the same function that we had previously, we had found the first derivative, isn't it? The first derivative was negative 2x, right?
Yes.
If we differentiated this again for the second time, what happens? You have negative 2, right?
Yes.
Which is less than what? 0.
0.
If the second derivative is less than 0, what do we find? What does that mean?
If it's less than 0, then
do we have a minimum or a max?
We have a maximum.
We have a maximum at the critical point, right? At that critical point, the function gives you the maximum. All right. Then we go to the other one, which was 2x positive. Derived again for the second time, you have 2 greater than 0, right? So it means that at critical values of x, the critical value of x equal to 0 is a relative what? Minimum. Because the second derivative is greater than 0, or it is positive, in other words. Your question should be, or the question must be, what if, sir, what if you have a higher function, a higher order function, maybe you have 2x squared plus maybe 3x. When you do the first derivative, what do you have? 4x, right?
4x, yes. 4x plus 3.
Now, let's see, let's put it 3 upwards. Let it be higher order function, okay? When we derive the first derivative, we shall have 6x squared plus what?
Yes.
6
plus 3 plus 6, yes.
Plus 6x. This is the first derivative. Then the second derivative shall be what? 12x plus 6. How do you know whether this function is a positive or a minimum? How do you know whether it's a maximum or minimum? That's why I say, what do you have to do?
You have to, I'm thinking, maybe you have to equate it to 0 and then solve for x.
All right. So, no, that was a good one. So the only that the
one
that
no. You have to, aren't you supposed to differentiate it again?
That would be 3 times. We only do twice.
Twice.
We don't have to differentiate it 3 times. Just twice. Okay. Now, yeah, I said when you differentiate it for the first time, you have to set it equal to 0. The first derivative is set to equal to 0, then you solve for the values of what? X. You get what I mean? Eh?
Yes.
Those are critical values, right? From the first derivative. Then if you found those critical values, Then
Mm-hmm.
those two critical values, you have to substitute them into this second derivative. Substitute where there is x, put that number. Then you check what you find, whether it's greater than 0, uh, less than 0.
Oh,
Did you pick that message?
yes.
So assuming that
Yes.
the
I
critical,
I I get it.
yeah, okay, that's fine. So assuming that the critical values were 1 and -2, we could have substituted the 1 into this second derivative. So it could have been 12 multiplied by 1 plus 6. That could have given us 18. 18 is greater than 0, meaning we have a what? A minimum, right?
Mm-hmm.
Then where we put a negative, the other at -2, at -2, the function would give us 12 minus 2 plus 6, which is actually 24 plus 6, giving us -18, right? Which
Mm-hmm.
is less than 0. This gives us a what? Maximum now. Please, this is the message we are sending across.
Okay.
Unconstrained optimization, single variable. This is unconstrained optimization. This is the same message I think we have already been talking about. Let's have a higher order. This is an example that I've already given. You know, the good part with the teacher, he always preempts. Yeah,
Mm-hmm.
he always preempts. Let's have it. Now the
Mm-hmm.
function is this one, x raised to the third degree minus 3x squared plus 2. How do we determine whether this function gives us the maximum or the minimum at critical, points or critical values? What do we do? Number one, we differentiate, right?
We
We
differentiate,
have to
yes.
find first derivative
3x.
and 3x, all that equal to what? We set it equal to 0 and
Mm-hmm. So
solve
for
for what?
x,
Solve for
x.
x first. Get the critical values first, and we know that
Mm-hmm.
3x is common. We'll have x minus what? 2, right? Equal to 0. We're solving the quadratic equation. And so that you
Mm-hmm.
can say 3x is equal to 0 and x minus 2 equal to 0. So that x can be equal to 0, right? And
Mm-hmm.
x can be equal to 2. You agree
Mm-hmm.
with us?
Yes, sir.
These are critical values.
Mm-hmm.
And how do we tell whether at 2?
Hello?
What do we do from here?
Hello? Oh,
Hi.
sorry, cut. Okay. So once we find the value for x, then we differentiate the second time.
Mm-hmm.
Yes. When we differentiate the second time, we're going to have 6x,
Mm-hmm.
6x minus 6. And
Or
then,
6x. Mm-hmm.
yes, 6x minus 6. And then now we substitute the values of x. So we substitute the values of x in the second derivative.
Which one do we substitute first? Which one do you want us to start with? 0?
We can start with
Obviously,
0.
when you substitute, we'll have -6, which is less than 0, which means that
Mm.
0 at 0 is the function minimum or maximum.
This one is maximum.
So at 0, the function is a maximum. Okay. Next, we can substitute the function at what?
At
By 2, right?
2. Yes.
It will give us +6 greater than 0, which means the maximum,
Mm.
the function is what?
A minimum. At 2, it's
It's a
minimum.
minimum function. Okay.
Yeah.
You are a sharp girl.
Thank you.
So this is what you have, you have fun. It's always nice to teach stars, She understands things so fast. Yeah, sorry
Mm,
that she rarely comes for class. Yeah.
Mhm.
Yeah, I was just wondering from the very first time, see, why does the stars understand things so fast? Then I learned that stars did is an accountant. So about here now, these are partial derivatives. Let me not talk about partial derivatives now, because this is what I was talking about in the afternoons.
Mhm.
Yes, where now we have more values of what? X on the other side. What do you
Mhm.
do? You get what I mean? On the right hand side, you have more variables. Here we have two variables on the right hand side. We have x1 and x2 and y. How do you differentiate those? You need partial derivatives now. You deal with partial derivatives. So at that
Okay.
point, how do you handle partial derivatives? This is exactly what I was talking about in the afternoons. So I can encourage us to go there and just
Mhm.
indulge. Then we come back again tomorrow. We start from unconstrained optimization of the multiple argument function, a multiple argument function where the variables on the right hand side are more than one now. You can even have four variables. You can have x1, x2, x3, x4, x5. It can be a long function. How do you really differentiate such a function? It could not be x1, x. It can be x, y. You can have x, y, w, u, maybe z. Five letters on the right hand side. How do you deal with them? So you need to
Mhm.
apply the partial derivatives, which is the conversation we had in the afternoons.